Something on Mars is moving. We have the photographs. We have the data. We have more than a decade of evidence. And somewhere along the way, the people in charge of the cameras seem to have quietly decided to stop talking about it. The pictures come from a spacecraft most people have never heard of, looking down on a planet most people think they understand. They show dark streaks creeping down Martian slopes, appearing in the warm months, fading in the cold ones, and returning year after year like clockwork. They flow. They behave like liquid. They look exactly like water running downhill. But Mars is not supposed to have liquid water on its surface. That rule has held for as long as we have studied the place. And whatever is making these streaks does not seem to care about the rule. This is the story of one of the loudest scientific announcements of the last decade, and one of the quietest retractions that followed it. It is the story of a discovery made by a 21-year-old, broadcast to the entire planet, and then slowly, carefully, walked back until almost no one was paying attention anymore. To understand what we are looking at, you first have to understand the camera that found it. In 2006, NASA slipped a spacecraft into orbit around Mars called the Mars Reconnaissance Orbiter. Bolted to its side was an instrument called HiRISE, the High-Resolution Imaging Science Experiment. The name is dry. The capability is anything but. HiRISE can resolve objects on the surface of Mars about the size of a kitchen table, from roughly 250 miles up. To put that in perspective, it is like standing in New York and reading the headline on a newspaper held by someone in Philadelphia. It can pick out the parallel tracks left by the rovers, wheel marks only a few feet apart, threading across the red dust. It has photographed the Curiosity rover from orbit, a tiny bluish speck at the end of a trail of tread marks stretching for hundreds of yards. It has even caught landers on their parachutes, mid-descent, falling toward the surface. For nearly 20 years, this single camera has been the closest thing humanity has ever had to a high-powered telephoto lens hanging permanently over another world, and it has returned tens of thousands of images, so many that there are not enough scientists to study them all. Much of what HiRISE has seen has been looked at, if at all, by only a handful of human eyes, which is part of how a discovery this large could sit inside the data, waiting until a 21-year-old happened to line up the right two frames. And in 2011, it found something nobody on the team had been looking for. An undergraduate at the University of Arizona named Lujendra Ojha was working his way through HiRISE images of the southern Martian highlands. He was barely 21 years old. He was not hunting for a discovery. He was running comparisons between photographs of the same terrain taken in different seasons. The kind of patient, unglamorous grunt work that fills the early years of a science career. What he noticed were lines on the slopes, dark, narrow streaks only a few feet wide, running downhill from the rims of certain craters. In one set of photos, they were there. In another set, taken months later, they had vanished. In a third set, taken a year after that, they were back, in roughly the same places. He flagged them and brought them to his advisor, Alfred McEwen, the lead scientist for HiRISE. McEwen looked at the data. They pulled more images from sites all over the planet, and the pattern held everywhere. The streaks appeared on warm, sun-facing slopes during the Martian summer. They grew, they lengthened, and then, as the planet cooled, they faded away, only to return the following year. They gave them a careful, cautious name: recurring slope lineae. The The scientific community calls them RSL. To the rest of us, they are simply the dark streaks that move. Consider what that actually means, because it should not be possible. The surface of Mars is, by every reasonable measure, dead. The average temperature is around -80 degrees Fahrenheit. The atmosphere is so thin, less than 1% of Earth's at sea level, that liquid water exposed on the surface should boil away into vapor almost the instant it appears. This is not a place where things flow. It is a frozen, irradiated desert that has been sitting still for billions of years, its great rivers and oceans long since lost to space or locked away as ice. And yet, here were features behaving exactly like flowing water. They began at a fixed point, the rim of a crater. They moved downhill, obeying gravity. They were governed by temperature, coming alive in the heat and dying in the cold. They were seasonal, as reliable as a calendar. If you had shown those same images to a geologist and told them the pictures were taken in Death Valley, the geologist would have glanced at them and said, "You were looking at a small spring seeping down a hillside." And here is what makes it worse. Mars was not always dead. The evidence is carved all over the planet. Ancient riverbeds, dried-up deltas where rivers once emptied into standing water, mineral deposits that only form in the presence of liquid water, vast basins in the northern hemisphere that many scientists believe once held an ocean. Billions of years ago, Mars had a thicker atmosphere, a warmer climate, and water flowing freely across its surface. Then it lost its magnetic field, the solar wind stripped its atmosphere away into space, and the planet froze. That is the story we tell. Mars had water once, long ago, and then it died. The RSL are a problem precisely because they suggest that story might not be finished, that the water did not entirely leave, that some of it is still down there, seeping out onto the surface on warm afternoons, 3 billion years after the oceans vanished. For 4 years, the team worked the problem. Behavior alone was not enough. Behavior could, in principle, be faked by sand or dust sliding down a slope, in some way nobody had quite worked out. To prove water, they needed more than motion. They needed chemistry. They needed to actually detect the fingerprint of water itself. In 2015, they got it. Using another instrument aboard the orbiter, a spectrometer called CRISM, which reads the chemical signatures in light reflecting off the Martian surface, they found something specific: hydrated salts, perchlorates and chlorates to be precise. Magnesium perchlorate, magnesium chlorate, sodium perchlorate. These particular salts matter enormously because of what they do to water. Mix them in, and they dramatically lower its freezing point. A perchlorate brine on Mars could stay liquid down to around -90 degrees Fahrenheit, well within the range of temperatures actually measured on those Martian slopes during summer. Ordinary water would freeze or boil. Salty water, cold, dense, and toxic, could survive, at least for a while. And the salts were detected exactly where the dark streaks were, and only at the times of year when the streaks were active. There is a grim irony hidden in those particular chemicals too. Perchlorates are toxic to humans. They interfere with the thyroid, and the Martian soil appears to be laced with them. So the very salts that might keep water liquid on Mars and might shelter microbial life are also one of the reasons the surface is so hostile to us. If there is something alive out there in those briny streaks, it is not just surviving the cold and the radiation and the near vacuum. It is living in poison, which, strange as it sounds, is not a deal breaker. On Earth, There are microbes that not only tolerate perchlorate, but actually breathe it, using it the way we use oxygen. If life ever took hold on Mars, a perchlorate brine is exactly the kind of hostile, salty, toxic environment where the toughest of it might still be clinging on. What happened next tells you how big this was. NASA did not simply publish a paper and move on. They called a global press conference, live broadcast, major news anchors, trending across every platform on Earth within the hour. The announcement was restrained in its wording and explosive in its meaning. Liquid water still flows on Mars today. Not in the deep past, not buried under the ice caps, not in some theoretical reservoir miles beneath the crust, on the surface. Now, in photographs taken last year, and the year before, and the year before that. For a few weeks, it was the biggest story in science. Every newspaper on Earth ran some version of the same headline. Mars has water. Maybe Mars has life. And then, very slowly, the story began to change. Because where there is liquid water, even briny, salty, half-frozen poisonous water, there is at least the possibility of life. On Earth, bacteria thrive in brines saltier than the Dead Sea. Some live sealed inside salt crystals in the Atacama Desert, the driest non-polar place on our own planet, surviving on the tiny amounts of moisture the salt pulls from the air. The discovery of RSL meant that for the first time, we had identified a specific place on Mars where you could, in theory, land a spacecraft and have a genuine chance of finding something alive. That should have been the beginning of a new era, a clean victory, the single most exciting target in the solar system. Instead, the agency went quiet. Almost as soon as the cameras switched off, other scientists began pushing back. Not on the data. The hydrated salts were real, the streaks were real, the seasonal pattern was real. They pushed back on what it all meant. And the same institutions that had been so confident a few weeks earlier suddenly developed a powerful appetite for caution. The first objection was the water itself. If the RSL were genuinely wet flows, they needed a source, something underground, recharging them year after year. But Mars has no rain, it has no rivers, it barely has frost. Where was all this water coming from? And how was it surviving in a near vacuum that should tear it apart? The second objection was the behavior of the streaks. Looked at closely, they only ever formed on slopes steep enough for dry sand to slide. They never crossed flatter ground. Real liquid water, even thick brine, should behave differently. It should pool, it should seep sideways. It should leave a residue behind as it dried. The streaks did none of that. In 2017, a team led by Colin Dundas at the United States Geological Survey published a paper offering a very different explanation. The streaks were not liquid at all. They were dry, granular flows. Tiny avalanches of fine, dark sand, triggered by some subtle temperature or atmospheric effect, creeping down the steepest slopes the way a layer of flour slides off a tilted plate. The hydrated salts were still there, still real, but perhaps they were simply sitting in the soil already, quietly absorbing trace amounts of moisture from the atmosphere overnight and releasing it by day in quantities far too small to call flowing water. Now read one line from the abstract of that paper carefully, because it does an enormous amount of quiet work. The authors note that if the RSL are mostly dry, then the volume of liquid water may be small or zero, which, in their words, alleviates planetary protection concerns about habitable environments. Translate that into plain English. If these streaks are sand, not water, then we no longer have to treat them as places where life might exist, and if they are not places where life might exist, then the legal and ethical rules that would force us to keep our contaminated spacecraft away from them no longer apply. The barrier to sending a rover there disappears, and so, conveniently, does the obligation to go look harder. That sentence did not appear by accident. The debate split the planetary science community down the middle. Both sides had good arguments. Both sides had real data. And both could point to images from high-rise showing exactly what they wanted to see. But in the public conversation, the dry sand theory was simply easier to talk about. It was less interesting. It made fewer demands. It quietly displaced the 2015 announcement in the public mind, and most people stopped paying attention. Mars, everyone agreed to assume, was doing what Mars always does, looking like one thing and turning out to be something more boring. What makes this genuinely uncomfortable is the timeline. We have a spacecraft in orbit right now, carrying the best camera ever flown to another planet, photographing a feature that has been visibly active for going on 15 years, and we still cannot agree on what it is. Not because we lack data, because the data is genuinely, stubbornly strange. Some RSL sites have shown spectral signatures consistent with water. Others have not. Some produce streaks that lengthen in ways that look exactly like fluid flow. Others grow in ways that look exactly like dry sand. Some appear on slopes facing the sun, where a brine might just survive. A few appear on slopes that should be far too cold for any brine to form at all. No single explanation fits every observation, and that, in itself, is telling us something about Mars that the textbooks have not caught up to yet. The most recent work tries to have it both ways, and it may well be right. The current best guess is that some RSL involve a small amount of water pulled from the thin atmosphere by those perchlorate salts, while others are entirely dry, and that the two processes might even happen at the very same site, in different seasons for different reasons. The planet that everyone had written off as a simple frozen corpse has, at minimum, one active surface process we genuinely do not understand. After more than 50 years of robotic exploration, after rovers and landers and orbiters and flybys, after billions of dollars and thousands of careers, Mars has held on to a secret in plain sight, right in front of our cameras. And we have made remarkably little effort to actually go and pry it open. Look at the machines we have on the ground right now. Curiosity has been driving across Mars since 2012. Perseverance landed in 2021. Both are nuclear-powered. Both can climb slopes, drill into rock, and run chemical analyses on whatever they find. Neither has ever been sent to an RSL. Neither has been allowed to. The official reason is planetary protection, the set of international rules meant to stop Earth microbes hitchhiking on our spacecraft and contaminating any environment where alien life might still exist. If there is even a chance the streaks are wet, then we cannot risk poisoning them with our own bacteria before we have had the chance to study them clean. That is a legitimate concern. It is also a remarkably convenient firewall, because it means that the single place on Mars where the question of life is most pressing is the exact place we have collectively agreed not to visit. And notice how the logic folds back on itself. To send a rover to an RSL, you would need to build it to the strictest cleanliness standards, sterilized to a degree that is enormously expensive and technically punishing. So the possibility that the streaks are wet makes them too dangerous to approach with the rovers we already have. But if you accept the argument that the streaks are dry, then there is no life to protect. and no reason to make the trip at all. Either way, you end up not going. The wet interpretation says, too risky to visit. The dry interpretation says, not worth visiting. Both roads lead to the same place, a rover parked a safe distance away, and a question left open. It is difficult to design a system more perfectly built to avoid finding an answer, even if no one ever intended to design one. The cameras keep watching from orbit. The scientists keep debating in the journals. The streaks keep flowing every summer, and the rovers, by design, keep their distance. And if this pattern feels familiar, it should, because Mars has done it to us before. In the 1970s, the two Viking landers carried experiments specifically designed to detect life in the Martian soil. One of them, the labeled release experiment, returned a result that looked on the face of it positive, a signal that matched what living microbes would produce. But other instruments failed to find the organic molecules that should have accompanied life, and the loudest consensus settled on a cautious no. The scientist who designed that experiment, Gilbert Levin, spent the rest of his life insisting the data had shown something real, and that the field had talked itself out of the biggest discovery in its history. He died still believing we had detected life on Mars in 1976 and looked away. See the shape of it. In the 1970s, a possible detection of life, downgraded to a maybe, then to a no. In 2015, flowing water on the surface announced to the world, and within 2 years, quietly downgraded to probably dry. Every time the planet seems to be on the verge of handing us something that would change everything, the conversation finds a way to redirect, to add a caveat, to wait. And it is worth being clear about just how much rides on the answer, because this is not a small argument about salt and sand on a distant hill. If life were confirmed on Mars, and if it turned out to have arisen independently, separately from life on Earth, it would be one of the most important discoveries in the history of our species. It would mean that life is not a freak accident that happened exactly once, on one lucky world, but something that emerges wherever the conditions allow, which would imply, by simple extension, that a universe of 400 billion stars in our galaxy alone is almost certainly teeming with it. A single microbe in a Martian brine would tell us more about our place in the cosmos than every telescope ever built. That is the size of the question sitting inside those dark streaks, and that is what makes the collective decision to look away so strange. We are not ignoring a minor geological curiosity. We are declining, for reasons of cost and caution and institutional comfort, to walk the last few hundred yards to the answer to one of the oldest questions humans have ever asked. Are we alone? Maybe that is simply how good science works. Extraordinary claims demand extraordinary evidence, and maybe the evidence on Mars just never quite crosses the line. Maybe there is no story beneath the story. Or maybe we have built a system that is extremely good at finding tantalizing hints on Mars and extremely bad at allowing itself to follow those hints all the way to a conclusion that would force us to rewrite the textbooks. Lujendra Oha, the undergraduate who first spotted the streaks, is now a planetary scientist at Rutgers University. He has spent more than a decade chasing the implications of what he found as a 21-year-old. In interviews, he is careful, measured, exactly as a scientist should be. But the question that drove him has not been answered. It has, if anything, been deferred indefinitely. We have even started picking targets. A region called Copratus Casma, part of the vast canyon system of Valles Marineris, has been studied as a possible landing site for a future mission. The plan being, at its simplest, to land near a streak, drive to it, drill into it, and finally look. The obstacles are real. Most RSL form on slopes too steep for current rovers to climb safely. Many sit in regions battered by dust storms or plunged into cold that would kill a mission outright. And planetary protection complicates every step. But the desire is there. The science is there. The streaks are there, year after year, dutifully photographed from orbit, dutifully catalogued, dutifully studied, and dutifully not investigated up close. Ask a planetary scientist in 1990 whether anything at all could be flowing on the surface of Mars today, in real time, observable from space, and the answer would have been a flat no. The atmosphere was too thin. The temperatures were too low. The planet was too dead. That was settled science. 30 years later, the photographs are sitting in the archives anyway. We do not know what makes the streaks. We do not know how they survive in conditions that should erase them. We can argue endlessly about whether they are wet or dry, but we cannot argue about whether they are there. Mars has always been good at this. It looked like Earth's twin to the astronomers of the 19th century, who imagined they saw canals. It looked utterly dead to the first flyby probes of the 1960s. It looked like a world that once had oceans to the orbiters of the 1970s. It looked like a sterile desert to the rovers of the 2000s. And now, in our own decade, it looks like a planet that is doing something on its surface that nobody quite expected. In plain sight, in the very place we have been pointing our best camera for almost 20 years, and where no one in charge seems especially eager to send a rover close enough to find out for certain. The probe is still up there. The streaks are still moving. And every Martian summer, somewhere on a slope facing the sun, something we cannot fully name slides quietly downhill, darkens the dust, fades, and waits for us to come back next year and watch it happen all over again. Whatever it is, it has been moving long enough that the young man who first photographed it is now in the middle of his career. It has outlived several missions and several theories, and it will keep moving, with us or without us, until someone finally decides that the answer is worth the risk of going to get it. That is the strange gift Mars keeps giving us. Not answers, just enough motion, just enough mystery, just enough reason to wonder why we keep choosing not to look. Subscribe to the Cosmic Deep for more of the stories nobody tells you, from the surface of hell to the edge of the universe.